Hi, it's Terry Dennery of the MathWorks. So in this demo, this video, we're going to explore kind of the operation of a staging system, right? And essentially it's a robotic arm, and its job is to move silicon wafers into and out of all kinds of equipment that basically embeds the silicon with the electronic circuitry for computer chips. All right. And I'll just say that in this industry, accuracy and precision of motion are extremely valued. Okay, so anyways, let's look at this inside Simulink. And so I'll bring up kind of the animation environment for this. Let's kind of reset it and let's rerun it. And so basically we added electric motors and we put in controls, and the voltage will be controlled to these motors to achieve the movement that we want. All right, and so it kind of begins with a commanded motion signal, and then that gets operated on to essentially make the robot do what it does. Right, that's a simulation of the electrical and mechanical components of the staging system. So here's our model, and here's what we just ran. And we essentially see it moving kind of in this XY plane, and that's why X and Y have interesting kind of range of motion, but the Z just kind of holds that position. All right, so what I want to do is kind of get beyond kind of um, a basic assumption of the mechanical motion simulation, which is that parts are rigid, and let's see what happens if they are allowed to deform just a little bit so they can vibrate. All right, and so I'm going to take this rigid version out. Actually, I'm going to jump in here a little bit just to kind of show you what we're working on. It's that gray piece right there, right? Right, and we're going to replace this rigid version with a flexible version, right? And so let's see, let's comment that one out. Let's bring this one in. All right, and I'll double click on it. So it's a little bit different on the interior. And you're going to see this little meshed image, which indicates it's an FEA kind of based solution, which means we ran an FEA calculation ahead of time and we figured out what these mass and stiffness matrices are. And it's through that that we're going to be able to integrate some vibration into the Simulink model. But let's not, let's just kind of keep it at that level, not dive too deep into the details of it. All right, and so let's rerun that simulation, and I'll hit the run button right there. Okay, and you'll notice, very quickly that we are seeing vibration is taking place, and we're going to see it in that Z measurement. And for the most part, everything looks pretty close to what we had previously, the X and Y certainly, and that when you realize that this vibration is occurring at the, the very minute scale that shows in this axis, that it's a minimal amount. And these parts are, they're pretty solid and firm and rigid. They don't bend much. And so this oscillation of, that kind of defines the vibration, it's happening at maybe about 1/100th of a millimeter. Okay. All right. Now we're MathWorks, right? And so we're good at analyzing things. And so I want to jump into this a little bit right now. I'm going to use this tool called the Simulink Data Inspector, right? And so, you'll see, axis 3, axis 2, axis 1. There's P, which is essentially the measurement, the feedback of that measurement, and C, which is the command, so how did we do? And so 3, 2, and 1 really represent the three motors that make this work. That the one that drives this first piece right here, that's called axis 1 motor. Then we got the axis 2 motor operating right there, and then we got the axis 3 motor that's kind of controlling this part that we are also modeling as flexible. All right, and so I'm going to bring all this back. Bring this back, and let's just work from here. Okay, so anyways, let's look how we're doing on axis 3. So I want to plot. Oops, I'll do the top plot. Okay, that's what we want to happen for axis 3. It's basically a rotation of pi over 4, which, whatever it is, about 45 degrees, I believe, that takes place in about 1 second. Yeah, so the x-axis is time right there. All right, so that's essentially the trajectory we want, and let's compare it to p axis 3. And we'll see that these curves pretty much lie right on top of each other. And so, from kind of a standard assessment of accuracy, this looks awesome, right? And but let's recall we're in the computer industry, and that the density of the electronic circuitry that will be embedded into these silicon wafers, it's measured at the level of like nanometers, right? And so what is it for a nanometer? I think it's like 10 to the minus 6 meters. I think that's where we're operating. So that their interpretation of what's an okay positional error is way beyond what normal requirements will be. All right. But anyways, it looks real good, and that error, which is the difference between these two, well, we're keeping track of that too, right? And so I'll show that right down here, right? And so with regard to these movements that are really in X and Y space that are associated with these rotations, you can see it a little bit better in the error function. So I just kind of dive in right there and you'll see that oscillation. Now this is a rotational thing, and so that whatever that is, on the order of like 0.0002, well, that's in radians, right? And that's really small, right? And with regard to kind of is that a problem or not? Well, let's kind of compare it to what we had in the previous simulation where we considered everything rigid, right? Okay, let's show that, maybe in different, oops, show that in orange. Okay, and that's where I wanted to get to, really, with this video, all right? And so my assertion is, wow, I think we got what we can do to help this industry to get better at staging systems, right? And what I'm getting at here is certainly kind of this really kind of tight kind of level here. We're seeing that the mechanical kind of deformation is occurring. It's small, but what I think is the most interesting is that little, vibration needs to be in this calculation. We totally need the mechanics, but we also need the electric motors. We also need the controllers to really figure out what kind of problem will this ultimately generate. And the fact that, a system where the parts are truly rigid uh, can reduce the error by, it looks like 90%. That this error, when we account for vibration being 10 times what it was before, that's the whole point. And you only can get that if you are, at least from I'll call it my conjecture, my presumption, is that little vibration is a frequency that's triggering some dynamics in both the electric motors and the controllers. You might think of it like a resonant frequency that's leading to much more substantial error. That's taking place, and you can only see that if you're properly accounting not just for the mechanics, but also the electronics of the motors and the controls and the things like that. Now, the additional assertion of why we feel we have something to contribute here is that we can do something about it. And so there's classic methods of tuning controls to deal with, frequencies that are problematic. Well, that's kind of what linear control theory is really all about, and it's certainly delivered quite well by things at MathWorks like the Control System Toolbox. So, anyways, we think we got a lot that we can do here to help. And we think the overall process of how we got to this model will be very interesting. And so we're recording additional videos. We'll show how we brought in the mechanics from the CAD tools like SolidWorks and CATIA and Pro Engineer and stuff like that to build these mechanical models, how we use tools for like finite element analysis and include vibration, but also how do you choose electric motors that are the right ones, how you develop controls, and ultimately, how do you get the real world? Because with Simulink, of course, a major part of our business, we almost describe ourselves this way, is we help you develop embedded software. And so what you're doing in Simulink ultimately generates code that will run on the microprocessors that can be employed on boards that will connect into the real machines. So anyways, we think we got a lot to, well, we're excited about the idea that we have a lot of things that we can help with, and we're looking forward to doing it. Thank you.